In this video, we'll be talking about ionization energy of elements, but we'll be focusing on successive ionization energies. We do know of what ionization energy is as the energy required to remove 1 mole of electrons from 1 mole of gaseous atom to produce 1 mole of gaseous ions. Anytime that we hear of ionization energy, we think of the first ionization energy because that is what is commonly used. There is ionization energy for each successive electron removed, and there can be as many successive ionization energies for an atom as there are electrons on it. But what happens if a second electron is to be removed, or a third, or a fourth? Let's consider the 13th element on the periodic table, aluminium, to get some clarification on successive ionization energy. Let us consider the 13th element on the periodic table. It is in the 13th group, just below boron, and it has 13 protons in the nucleus here, with 13 electrons in its electronic configuration and 3 valence shell electrons. Now, if the first electron is to be removed, we will be left with 12 electrons. It means that it has lost 1 electron. With this ion, with a +1 charge on it, it means that it has lost 1 electron. So it will be left with 12 electrons on this ion here. Now, this ion here with the +2 means that it has lost 2 electrons. And so we will be left with 11 electrons on it. And this +3 charge means that this atom has lost 3 electrons and will be left with 10 electrons on it. Now, if a 4th electron is to be removed, it will be removed from the core electron, from an inner principal quantum energy shell. Now, the more electrons are removed, the smaller the size of the atom. Now, because the fewer the electrons, the greater the nuclear influence on the remaining ones. It means a greater grip on the remaining ones, and the more firmly or tightly the remaining electrons are held. And so the more electrons are lost, the smaller the ion becomes. Generally, cations have smaller sizes compared to their neutral atoms. But the more positively charged the ion becomes, the smaller the size of the ion. And it means a greater influence from the nucleus on the remaining electrons. And it also means a greater energy that will be required to remove successive electron or the next electron. Now, if you consider aluminium and you want to measure its ionization energy, or for any element you want to measure the ionization energy, it's important to note that the condensed form should be converted to the gaseous form. It is important to take note of that when you are asked to write the chemical equation of the first ionization energy. You make sure that the element is in a gaseous state. Because when measurements are done in the condensed form, whether it is the solid or the liquid form, the energies that will be measured as ionization energy would include the ones that will be used to break intermolecular bonds and other interactions. And so it is important that it is converted to the gaseous form, because in the gaseous form, it allows for isolation of the atom. It minimizes intermolecular interactions that would interfere or distort the measurement. So when you're asked to write the chemical formula representing the ionization energy of elements, you make sure that they are in a gaseous state so that you have your full marks. Now, this equation means that with a gaseous aluminium atom, when you remove an electron from it, you will be left with 1 mole of gaseous +1 ion. And that energy required to do that is 578 kilojoules per mole. Now, ionization energy is measured in kilojoules per mole. It is also sometimes measured in electron volts. By the way, 1 electron volt is equal to 96.485 kilojoules per mole. So the first ionization energy is when the first electron is removed from a gaseous atom. So when you are asked to define what first ionization energy is the energy required to remove 1 mole of electron from 1 mole of gaseous atom to produce 1 mole of gaseous plus 1 ion. Now, when you are asked to define what second ionization energy is the energy required to remove 1 mole of electrons from 1 mole of gaseous plus 1 ion to produce 1 mole of gaseous plus 2 ion. Now, when you're asked to define what the third ionization energy is the energy required to remove 1 mole of electrons from 1 mole of gaseous plus 2 ions to produce 1 mole of gaseous plus 3 ions, and so on and so forth. And so get used to the definitions. Don't be confused. When you are asked to write the chemical equation for the first ionization energy without specification to a particular element, you can write this for your answer. And that will be the general equation that would represent the first ionization energy for any element. But when a particular element is specified, you just indicate the element symbol and you just get the equation written accordingly. Now, you can see that the first ionization energy of aluminium is 578 kilojoules per mole. The second ionization energy is 1820 kilojoules per mole. And so subsequently, progressively, you realize that the ionization energies increases. Now, ionization energies are always positive because it involves the supply of energy to overcome the attraction force between the nucleus and the electrons on them. So, and because of that, ionization energies are always positive, and the process is an endothermic one. It is important also to note that successive ionization energies are greater than the previous ones. If you look at aluminium, the second ionization energy is greater than the first, and the third ionization energy is greater than the second. And so subsequently and progressively, the ionization energies of elements increases, because removing the next electron means more energy is required in order to achieve that, because the forces of attraction, as you remove successive electrons, have greater influences on them, and so it requires greater energy to remove them. Now look at the difference. If you look at the difference between the second ionization energy and the first ionization energy, you realize that it is not a common difference. It is not a common difference. The difference between the second ionization energy and the first ionization energy is about 1,200. It's about 1,200. Now, the difference between the third ionization energy and the second ionization energy is about 900. And so we do not have a common difference between the ionization energies, but you see a gradual increase in their ionization energies. Now look at aluminium. Look at the difference between the fourth ionization energy and the third ionization energy. We have a difference of about 8,800 here. Now, why is that so? Why is it that from the first ionization energy we have a difference of about 1,002, the difference between the third and the second we have a difference of about 900, but the difference between the fourth and the third is such a huge jump of about 8,800. What is causing that? What is accounting for that? Now, the reason why it's so is that The first three ionization energies involves the removal of a valence shell. Now, the removal of a fourth electron would mean removing a core electron in an inner principal quantum energy shell. And that means that the attraction on that particular electron is very strong. It is closer to the nucleus. The nucleus has a stronger grip on it, and it will require a substantial amount of energy to remove that. And so when you look at successive ionization energies, it gives you a clue as to the number of valence electrons on the atom. It gives us a clue as to the group in which the element is in. Now, using aluminium as an example, the first three ionization energies involves an increment, not a substantial. There is an increment all the same. When we are able to identify a huge jump, that huge jump will give us an idea of the group within which the element is. So when we are able to know the successive ionization energies of elements, we are from those figures able to determine or predict the group in which the element finds itself in. Whenever we identify a huge gap, a huge jump, it means that electron is being removed from an inner principal quantum energy shell, and that will give us an idea of the group within which the element is most likely to be. So with this, let's try our hands on a few exercises to identify the group that elements provided could possibly be. We may be confronted with such questions in our chemistry class, that the successive ionization energies of elements are given, and we are supposed to determine, giving some data of ionization energy values of the elements, and we are supposed to use these values to determine the most likely group that the element finds itself in. So we have been given elements A to F, and that is to say we have 6 elements over here, and our assignment is to determine the group for each element. So what we're going to do is that we're going to scan through the values that has been given to us for each element, and we will be looking for a big jump of the ionization energies given us. We should also take into account that the successive ionization energies of elements are always higher than the previous one. They are always positive. So when we scan across the ionization energies, we're going to see a gradual increase. Of course, what we're looking for is not the ordinary increments in the ionization energies. That is normal for successive ionization energies. What we're looking for is a huge jump, and when we are able to identify that huge jump, it will give us an idea. That amount of energy is expended in removing a core electron, and that all the previous energies provided has been used in removing valence shell electrons. So with that idea, we go into determining the possible groups that the elements A to F are. So let's start with element A. Now, the difference between the second ionization energy and the first for element A is about 791. Between the third and the second is 1655. Between the fourth and the third is 1124. Between the fifth and the fourth is 11,735. So from here, we are able to observe that the huge jump occurs with the fifth ionization energy. And that means that this amount of energy is used to remove a core electron. All the previous energies, 786 is used to remove the first electron, 1577 is used to remove the second electron, which is a valence shell electron, 3232 is used to remove a valence shell electron, 4356 is used to remove a valence shell electron, but 16,091 is used to remove a core electron. So it means that the first 4 energies are used to remove valence shell electrons. So it means that there are 4 valence shell electrons for element A, and element A is most likely to be in group 14. For element B, the difference between the second and the first ionization energies is 896. Between the third and the second is 1003. Between the fourth and the third is 2050. Between the fifth and the sixth is 1310. Between the sixth and the fifth is 15,000. So the huge jump occurs here. The huge jump occurs here. In the previous example, the huge jump occurred over here. So with element B, we are observing that a lot of energy is used in removing the 6th electron. That means that the 6th electron is a core electron. And all the previous 5 electrons are valence shell electrons. So element B is most likely to be in group 15. For element C, the difference between the second ionization energy and the first ionization energy is 4066. So we are observing a very huge jump for the second ionization energy. We can observe a huge jump over here. And so based on this huge jump, we are able to conclude that element C is in group 1. Now for element D, the difference between the second and the first is 713. The difference between the third ionization energy and the second ionization energy is 6,282. And we can observe a huge jump between the second ionization energy and the third ionization energy, which gives us the clue that this amount of energy, this 7,733 kilojoules per mole amount of energy, is used to remove a core electron. These first two ionization energies are used to remove valence shell electrons. And so element D is most likely to be in group 2. Now for element E, the difference between the second ionization energy and the first is 1,239. Between the third and the second is 928. Between the fourth and the third is 8,832. And so the huge jump occurs for the fourth ionization energy. And that would mean that this amount of energy is used to remove a core electron. The previous first 3 ionization energies are used to remove valence shell electrons. So element E is most likely to be in group 13. Now with element F, the difference between the second and the first is 930. Between the third and the second is 900. Between the fourth and the third is also 900. Fifth and fourth is 2,100. The difference between the sixth and the fifth is 1,000. Now, with these differences in their ionization energies, we are unable to determine any huge jump from the first to the sixth ionization energy. It is ranging between 900, between 1,000 and 2,100. There is no substantial jump between any of the successive ionization energies. And the data that we have here is only limited to the 6 valence shell electrons. So what if the huge jump comes with the 7th ionization energy or the 8th ionization energy? We are unable to tell. So we can safely predict that element F can either be in group 16 or group 17 or group 18. So element A, most probably in group 14, element B, possibly in group 15, element C, group 1, element D, group 2, element E is probably a group 13 element, and element F could either be group 16 element, group 17, or group 18 element. So this is the end of my video. Thank you very much for watching, but keep watching.